Okay, last time we working on decibel. Any question regarding to the decibel? If it's not, then we going to the next one. Okay, let's see. I already saved Telcom. Okay, last time we already talking about differential amplifier. Quickly go through it, okay? Let's see, you can see on this picture here, if you get the both input routed at 0, then the output will be the same, okay? And we already telling you, if you apply input to the V1, that means the input 1. Then the Q1 will be common emitter, okay? And Q2 will be common base. Okay, so you can see that sideway connect to the VB1 and also VB Q2 will be routed. Okay, so one will be common emitter, the other one will be common base. And they just display for you the output how they look like. Okay, VC1 will be less than VC2. And if you try to revert it, that means you apply to Q2 and Q1 will be routed. They just come in reverted. But the thing is, if you get the sine wave in the Q1, then you get the sine wave at the output 1. However, they will be reverted. And the output 2, they will be in phase. Okay? The same thing if you revert the apply. Now, mode of signal operation, single-ended. Okay, they can be a single-ended input or the output. Single-ended, that means you apply only one input and the other input will be routed. When the differential amplifier operates in this mode, one input is routed and the signal apply only to the other input. Okay? Differential input. Two opposite polarity, our phase, signal apply to the input. If you want to apply input 1 and input 2, only thing they asking you, they have to be opposite. You see this one going up and this one have to be going down. That's what they asking for if you want to apply to both input, input 1 and input 2. Now, common mode input, both inputs are the same phase, same frequency, and the same amplitude are applied to the two input. That means this and this one identical. Okay, the output are superimposed and they are canceled out, resulting the output will be 0. Okay, So they consider this input will be the noise. So the op-amp, when they're looking at the input, they're identical and they will be rejected. So the output will be 0. Okay. This action we call common mode rejection. Common mode rejection means that the unwanted or the noise signal will not appear on the output for the desired signal. Common mode signal generally are result of the pickup of radiated energy on the input line of the adjacent line. That means they coming out from normally the power. Okay, they create a variation signal, and they will be identical to the both input of the op-amp, and the op-amp able to cancel that out. Common mode rejection ratio, the measure of the amplifier's ability to reject common mode signal, is a parameter called common mode rejection ratio, CMRR. Okay, and they will calculate by the formula. You take CMRR equal AV. That means the gain of the differential amplifier divided to the gain of the common mode amplifier, where ADV differential voltage gain and ACM is common mode gain. The higher CMRR is the better. The CMRR is often expressed in the decibel in a dB. If you want to convert a common mode rejection ratio to the decibel, apply the formula 20 times log of AVD divided to ACM. Okay, they give you example. A differential amplifier at a differential voltage gain, AVD equal to 1000, and a common mode gain, ACM, 0.2. They want to know the CMRR and express in decibel. So CMRR equal AVD divide ACM, 2000 divide 0.2, you get a 10,000. And now you convert it to the decibel. Take 20 times log of 10,000, you get 80 dB. Okay, and another one, who done that? Just telling me. You want CMR. Okay, equal AVD. Divide to the ACM. And that will be 850 divided to 0.25. Okay, see what you get.
$34,000.
34,000. And now you want that to be in dB. Okay, 20 log. Time log of 34,000. What you get?
About 90.6 dB.
Okay. 90.6 dB. Okay, so that's a very simple thing. Everyone have to know how to do the calculation. You know, just a formula. They given you the formula and you're able to calculate it, then you can be converted to the decibel. Now, differential amplifier. For the differential amplifier circuit, so they show to you what? This is the noise right here. You get the V, that means VCM means common mode. Those signals will be identical. Okay? They connect into input of the differential amplifier. Okay? They're given here. Given AVD 2500 and CMRR 30,000. V in 1 equal 500 micro VRMS. At the same time, 1 volt 60 Hz common mode interference signal appear on both input. So basically, this is the 1 volt 60 Hz. And the other one only 500 micros. So nowhere you can say the 500 microvolt inside the 1 volt. Okay, the thing is that your signal is too small. So the op-amp try to do is try to delete the 1 volt 60 Hz at the output. Okay, now they say the number 1 determine the common mode gain ACM. On this one, I already given you the calculation. Common mode rejection ratio equal AVD over ACM. That means from that formula, you already get the CMRR. You're able to calculate the ACM. So ACM equal AVD divide CMRR, and you get 0.083. Okay. Then they say express the common mode rejection ratio in dB. Okay. So you get the common mode rejection equal 30,000. And now they want it to be in decibel. Then you apply 20 times log of 30,000. You get 89.5 dB. Okay, and they want to know, determine the IMS output. Okay, V in equal V1 in 1 minus V in 2. Okay, so V in 2 you have a no signal. Okay, V in 1 500 microvolt minus 0, you get 500 microvolt. And V out will be AV times V in. That means 2500 times 500 micro VIMS, and the answer will be 1.25 VIMS. Any question for this example?
And Mr. Pham, I thought common mode rejection ratio was independent of the differential gain. So if isn't the common mode rejection ratio 20 log of the analog rejection ratio?
What do you mean? Okay,
Shouldn't,
yeah, go ahead.
okay, well, I think for your answer A, you're calculating the ratio of the differential output to the common mode output. But the common mode rejection ratio, I think, should just be, in dB, should just be 20 log, or minus 20 log of 30,000. Am I wrong?
Okay, Cm equal AVD, right? ACM. Okay,
Well, that's the question I'm asking. Is that the right definition?
this is the right definition.
Okay.
This is just a definition. We can make anything different. Okay, in this case, they given you 30,000. And they only want to know what the decibel for this CMRR. So that's why we take CMRR 20 log of 30,000. Now, if you can understand, you can try to understand this thing. This one will be a different from the previous one. They apply input 1 and input 2. Okay, they say input 1 equal input 2 equal 500 micro via ms. They the same value. However, if you're looking into the signal, they opposite. This one going up, this one going down. Okay, they must be 180 degrees of phase. If they in phase, the same value, same frequency, they consider that will be a common. Okay, so at the same time, 1V, the same thing on the other one. Okay, 60 Hz common mode interference signal appear on both the inputs. They want to know the VIMS output, and now V in different equal V in 1 minus V in 2. V in 1 at 500 microvolt, and V in 2 will be opposite, minus 500 microvolt. So that's why you get 1 millivolt. Then V out will be equal AVD times V in different. AVD is 2500 times 1 millivolt via ms, you get 2.5 volt IMF. Determine the V, the IMF interference voltage on the output. Okay, ACM equal V out divide V in CM, and V out CM equal ACM times V in CM. Okay, V in CM, we already, the gain, we already know that the 0.083, and the voltage for the common is 1 volt, and that's why you can get 83 millivolt. Only thing I want you to make sure you understand is whenever both input get the same signal, same frequency, same amplitude, that's considered to be the noise. That's a common mode. And if any signal going to apply into both input of the differential amplifier, they must be different phase. Okay, they must be opposite phase. Okay, so we're done for
Mr.
this
Pham.
one.
Mr. Pham, can you go back to that slide? The very last line is say V out is equal to ACM times V in, which is equal to 0.083. Now, how do we get 0.083 again?
We already calculated here.
Oh, it's the same problem. Oh, okay.
Yeah, same problem.
Okay, okay.
Only thing is they apply 2 input instead 1.
Right.
Okay?
Yeah, thank you.
You're welcome. Okay, now we go with the differential amplifier. Now, op amp. Let's see. Operation amplifier. Okay. When you see this symbol, and you know this what they call op amp operation amplifier. What's going on inside here? On of the transistor inside. Okay. Normally they're using NPN transistor inside to build the op amp. Okay, first thing they say they get a 3 terminal. Okay, one go into the negative here. They call it inverted. Input, that's just a name, and you must know. Otherwise, they asking you don't know what the name. And the one go to the positive, they call it non-inverted. Okay, and they already telling you here, right? Non-inverting input plus sine output. To power supply, normally you can get a one power supply here, plus V, and one in here, minus V. Okay, that power supply they can going from plus 8 volt to 38 volt, or minus 8 volt to minus 38 volt. In lab, we're using 15 volt or 12 volt. Then that will be minus 15 volt. Okay. And the voltage VD they call it different voltage. Input different voltage. Differential input. VD, by definition, they have to be equal V at the positive minus V at the negative. Okay. Now we can tell you for the ideal of an open loop gain. We will be get 2 loop gain. One will be an open loop, and one will be a closed loop gain. Open loop gain means op amp itself. You bought it, op amp, you get an open loop gain. Okay, without any connection. Open loop gain, they want it to be infinity. Okay, input impedance, that means the inside here, they want it to be also infinity. Oh, output impedance, that output impedance, they want it to be 0. Okay, and also they say differential input VD equal V in at the positive minus V in at the negative equal 0. That's what they want. Okay, let's see what in here. Okay, let's see. We are number 1 right now. Okay, at the page. Okay, I want to explain to you here. Negative, positive. Okay, I can say V1, V2, or VB, VB, VA. That doesn't matter the name. You can say V1, or you can say VA and VB, and that will be VR. So for the ideal op amp, they want the gain. They say AOL, open loop gain. Okay, and for the ideal, they want it to be infinity, a big number. Okay, and also the voltage between VA and VB, VD will be equal VA minus VB all the time. VS positive minus VS negative. And VS negative here they go inverted. Input. On this side, it's a non-inverted. Okay, so when they're talking about non-inverting or inverting, you know which one. And for the ideal op amp, they want the gain AOL equal infinity. Okay, and they want input impedance GE is infinity. This is O. G out 0 O. That's what they want. Okay, and they want VD equal VA minus VB will be equal 0. And now, let's see.
Open, no.
What VD by definition? What is the gain? Differential gain equal what? You know,
Infinity.
in general,
VA minus VB.
no, in general,
Voltage
okay,
drop across a component.
I just talking about in general. V out equal, no, gain, sorry. Talking about gain. Okay, AV. V out divide, right? That's a very basic definition. The gain, that means the ratio between output and the input. And now in this op amp here, VD will be equal what?
VD.
V out, right?
V out over VD.
Over VD. Sorry. Ah, man. I'm talking about, let's see, A O L equal V out divide to VD.
Equal to infinity.
Yeah, that will be, you wanted infinity, right? However, from this formula, I want VD. V out divide A O L, right? And I can be equal V out divide to infinity, correct?
There's nothing, Mr. Pham, there's nothing in an open loop amplifier that controls, there's no feedback to control VD. Right? If you put VB and VA into the amplifier without feedback, VD is VB minus VA and V out will be what it is.
Yeah,
But you
VD,
can't,
by definition, VD equal VA minus VB.
yeah.
Okay,
And without feedback, there's no
Yeah.
control on the difference. You can't drive VB minus VA to 0 without feedback,
now,
right?
right now I try to prove for you, how come VD equal VA minus VB will be equal 0? That's what I try to prove that. Okay, so now if I said, try again. A O L equal definition will be V out divide to V D. Is it correct?
What, I can't read the first, what's the first term? A what?
A
Open loop?
AOL.
Oh, okay.
Okay, sorry.
Yeah, and that's equal V out over, I mean, without hitting the rails, V out over VD is equal to infinity. Because the gain is
Okay.
equal to infinity in an ideal operational amplifier, right?
So AOL equal V out divide, correct?
Divide by 0. Divide by 0.
No,
What you want, what I said, what you want that for ideal?
then it should divide by 0, V over 0, you will get infinitive.
Yes.
So that's why you come up with equal. Is it correct?
No,
No.
Oh, why not? And the
This
number
equation,
divide. And
this
the
equation
number,
is correct. Anything divided by infinitive is 0.
that's what I said.
no, okay. But
No,
Mr.
but the
Pham, look at your equation for A open loop. You say up here with the circle, A open loop is equal to infinity.
That's
And
what
then
they
down-
want.
Right, and then down here on the lower left, you say AOL is equal to 0. Those two equations cannot both be true.
You say AOL, okay, equal, okay. That's what I have to do in this one right here. Sorry.
Yeah.
I think all I'm saying is that you can't do these calculations with the open loop amplifier because everything there's nothing to control VD with
Okay.
feedback. So
Now-
all you can say is that if VB minus VA is anything but 0, V out is infinite.
Okay, I get this one correction there. V out divide A
AOL.
divide to AOL. This correct or not?
Yes, is equal 0.
Right, that's what I try to prove they will be equal to 0. That means VD
That-
equal to 0. That will be telling you what? VA equal VB. The thing is VD equal VA minus VB. And
I think, sorry, I apologize for arguing, but I think you're confusing cause and effect in an open loop amplifier. The V out has has no control over VB or VA. VB and VA is what it is. Let's say VB is 5 volts and VA is 1 volt. I can do that. There's no control from VO on the input, right? So the VD would be 4 volts. I don't care what VO is because it can't influence.
no, the thing
VB and
is the
VA.
IC. This is basically they build for the IC. Okay. Only thing is they just try to make sure the VD have to be the difference between VA and VB. And ideal, they will be equal 0. That's what I want you to know. You cannot tell what the output is supposed to be. We don't have they build inside the op amp. We not connect anything into the op amp yet. If you want to working on op amp and make sure you understand the difference between two input, they will be equal 0. That only telling you VA and VB will be equal.
Mr. Pham, I have a question.
Yeah,
This op-amp is useless if you don't do the looping feedback connection. It has no meaning. This is all ideally we are talking about. Am I right?
yeah, right now we're talking about open. They have nothing at all. That means that the IC itself.
So without feedback connection, without connection, it's a useless.
That later when we go to the feedback connection.
Okay.
Only thing we bring it up here is remember, VD means the difference between voltage at positive and a voltage at a negative, okay? And they will be equal 0 all the time when you analyze for the op amp. Okay, let's see. This is just the same thing. Now, practical op amp. This is the one op amp we will be working on. Output voltage V out equal V in positive minus V in negative times AOL. That means VD times open loop gain. VD, that means the difference between two inputs. The gain AOL open loop gain for 741 op amp close to 200,000. That means open loop. Output of op amp is never higher than the power supply. Okay, no man, you can see the gain of the open loop is 200,000. That not mean we apply 1 volt, you can get 200,000 volt. Okay, the reason is they're telling you the output op amp never higher than power supply voltage. If you're using 15 plus 15 volt minus 15 volt, then the output op amp cannot be higher than 15 volt, no matter what, okay, or minus 15 volt. When input applied is too high, that force the op amp into saturation, okay, and the op amp output will be equal plus or minus saturation voltage. That saturation voltage will be less than power supply around 1.4 volt. Open loop gain is defined as the amplified output amplification without any external feedback signal connect to it, and for a typical operation amplifier is about 100 dB at 0 hertz. Okay, now in order to solving that thing here, I need giving you the example. Okay, now you can see I get this op amp, okay, with the gain AOL. $200,000. And the power supply saturation, I using 15 volt, okay, and minus 15 volt. So in here, they given you input positive, input negative, okay, and they want VD. So that is VD right here. VD equal V positive minus V negative, okay? And if you want to get the V out equal AOL times VD. Is it right?
Yes.
Okay. First thing we assume they will be saturation. So when they be saturation, what happened? Then V out can be plus 15 volt or V out can be minus 15 volt. Okay. We said the output cannot be higher than power supply. They can be equal plus positive saturation or minus saturation voltage. So I said, okay, we assume they will be saturated. V out equal 50. Then we want to know what the VD is supposed to be. Okay, we already know VL equal AOL times VD. Then VD will be equal VL divide AOL, right? Okay, so for the first, they saturate 15 volt. Divide 200,000. What you get?
25 microvolts.
15 divide 200,000, 75, right?
75 microvolts.
Yes, 75.
Okay. That means output at the positive saturation. And now we need to know VD, VL divide AOL for negative saturation, minus 15 volt, divide 200,000. They will be minus 75 microvolt. Okay. And then we try to see that will be a VD. And right here will be 0 volt. Okay, so you get the VD equal 75 microvolt right here. And minus 75 volt right here. Now, any voltage VD going into this side that means op-amp be saturated. Okay, that will be plus saturation. Any voltage VD on this side, they will be minus VD V saturation. Only thing is from any voltage less than 75, higher than minus 75, they will be VL, they will be AOL time VD. In order to know the value of the VD, okay, based on what they given to you. But you have to know the limit for the VD so they can be saturated. Now in here, they give an input positive, input negative. What VD equal? Tell me.
Negative 20.
20
Negative 20.
minus 20. Okay, so the first one you calculate a minus 20. That means they will be inside here, right? They less than 75 and also they greater than minus 75 microvolt. So what we out?
Minus 4 volts.
That means you take a 20 microvolt times 200,000, you get minus 4 volt. All right? Okay, now go ahead and do the rest for me to see how many people can understand.
Can you go back to your?
Second one is 70 VD, 70 microvolts.
Can you go back to your formula page here, please?
What?
Where you were doing your formula breakdown, can you go back to that page, please?
So it turns out if the differential input voltage is between plus and minus
Right.
75 microvolts, the output is the open loop gain times the differential input. But if the differential input is greater than 75 microvolts, then the output is limited to either plus
Or minus
VDD or minus VDD.
with saturation. Okay. Number two, what VD? Is that 70?
Yes, 70 micro.
Okay, what we out? That means you want to calculate the V out. They not be saturated, they can be time 200,000. I think they can be 14, right?
Yes.
Next one.
Minus 20 microvolt.
Yeah, minus 20. And that will be minus 4, right?
Yes.
Next one.
140 microvolt.
140. Perfect.
So saturated. So therefore only 15 volts.
Is it a minus 145?
Yes. So saturated. So it's minus 15 volts. No, 65 volts, 65 microvolt.
What number? 6?
65.
Yes.
Is it 13, right?
13 volts, yes.
That one.
Minus 100 microvolts. So that's saturated.
Minus 15 volts.
The last one is 40 microvolts. So it's equal to 8 volts.
Perfect. Make sure if you not follow it, go ahead and ask, okay? Otherwise, your test or your quiz, you have to do it.
Yeah, could you explain how you're breaking that down?
How do
Minus 40
I,
is negative 20.
Mr. Pam, could you explain how you're coming to the VD?
how do I get the VD, right?
Yes, please.
VF positive. Minus VF negative. So the first one, you get 20 at the input positive. And you minus to 40,
Okay, got it.
okay?
Yeah, okay.
Yeah, make sure it's clear for everyone. It's not hard to do.
Okay, thank you.
You're welcome.
I think the lesson here is that the output voltage of an op amp cannot exceed the supply voltages.
Right,
So if you take, right? Right. So if you take the differential input and multiply it by the open loop gain, if the open loop gain makes the output greater than the supply voltage, then the supply voltage is the output. But if the open loop gain times the differential input is less than the supply voltage, then the output voltage is the input voltage, the differential voltage times the open loop gain. So it's like a you're bouncing between the two walls. As long as the input voltage difference is small enough to stay between the two walls of the supply voltage, then you're good. But as soon as you increase it, you hit the wall.
that's what in here. Right? First thing you have to know what saturation voltage they given out. Normally they will be less than the power supply. So in order to do the calculation, then you have to assume if they saturated, what the limit for the input VD. That's why I said VD equal 15 volt divided 200,000. That's the limit for the VD between active and saturation. That means any VD higher than 75 microvolt, they will be saturated. And when you say they saturated, then you cannot using the gain 200,000 to multiply by VD. They have to be equal that saturation. That's why, the people is not afraid to working with the op amp. When you say they get a 200,000 gain, they apply 1 volt, they get a 200,000 volt. No one can be working on that situation. So that's why op amp all the time, when you apply the input, it will be forcing the output to saturation. That means no matter what, output have to be less than the power supply. Normally, power supply using 15 volt or 12 volt. So if you get that problem again, you know how to do your calculation. Okay, input signal. Okay, single-ended mode. They given to you. They just explain to you. Single-ended mode, that means you apply only one input. The other input will be routed. Okay, either way, you apply into negative, positive route. Apply to positive, negative route. That's what they call a single-ended. Then this one is a differential input. That means you apply signal to both input. Only one thing they will be asking you. Input, they must be out of phase. One going up, the other going down. Okay? Otherwise, they will be mismatched to common mode. Okay, let's see. Output offset voltage. Okay, if we connect op amp this way, what output?
What?
If I connect the op amp on this way, this I show you here, what the output supposed to be?
Are they
Zero.
both grounded?
Right,
Zero
what I know
with
right here.
with no offset.
Zero.
Zero. That's a normal, right? If we connect both input to the ground, output supposed to be zero. However, if they not zero, that means they get the offset voltage. Okay, like they get 10 millivolt. They supposed to be zero, but they not. They get 10 millivolt. That is the offset voltage. Okay. In order to do, you can see op amp 741 pin 2 negative, pin 3 positive. Now you get a pin 1 and pin 5 that they will be connected to the potential meter. Okay, the port. You can adjust this port to guarantee you get a 0 volt at the output. That is into adjust the offset voltage. Normally, when you're working, sometimes you can see they can get that variable resistor connect to pin number 1 and pin number 5. So if you measure the output, they not 0 volt, then you can adjust that resistor until they get 0. That means the offset. I believe you're working on the left volt. You get a chance to do it. Okay. They say adjust offset voltage. Connect the port to pin 1, pin 5. Connect both input to the ground. Adjust the port until Vout closes to 0. Sometimes you cannot get exact 0, but they can down to 1 millivolt or microvolt. That be good enough. Okay. Now open loop and a closed loop op amp configuration. On the left side here, we already see open loop. That means op amp itself, no connection at all. And you get the AOL. AOL means open loop gain. And they be ratio between V out divided to V in. And V in here, basically same thing with VD. Difference between positive and negative input. Now, closed loop gain. Okay, that means now you connect the resistor here from the output into the negative input here. Okay, and now this will be closed loop gain. That means you can see more detail on this circuitry, okay, later on. Only thing we bring up here for you to understand how the open loop working and how the closed loop working.
Mr. Fan, I have a question.
Yeah,
In the real world, people use the open loop
no,
configuration.
not open,
Okay, never open.
never.
Okay.
Open, that's just a op amp, you go to buy it, you get it, that's it. No connection, so they're not doing anything.
Okay.
They're working with the closed loop. Now, try to understand this thing. Open loop frequency response curve. Okay, let's see. I need that thing. Man. Okay, let's see, page number 9 here. Okay, asking you about the bandwidth. What is the bandwidth?
Low side, high side, center carrier.
Basically, the definition for the bandwidth, that means equal amp frequency maximum minus frequency minimum. Basically, the range of the frequency, okay, they can be transmitted the signal. What is the bandwidth of the voice?
Standard bandwidth of voice is 3 kilohertz.
What is the bandwidth? That's just telling you for your voice, they can transmit it on what frequency?
8 hertz to 20K.
Okay, so basically your voice, they will be going from 10 hertz up to 20K. Okay, so the bandwidth, that means they allow a certain frequency can go. And then we already know what is the critical frequency. You know what is critical frequency? FC equal
Top.
It's where the response is reduced by 3 dB or 1/2.
yeah, but what the formula to calculate the cutoff frequency, critical frequency, or stop frequency? Let's see, I try to memorize. Oh, 1 over what?
Is it 1/2 pi RC?
Okay. I given you example here. This is circuit. And the signal coming in and the signal coming out. Okay. I can say you get 5 volt, 1 kilohertz. Okay. When they coming out here, if you get VL equal 5 volt, That means you not lost any voltage. Whatever coming in will be coming out. Okay. However, if you get V out coming out only 3 volts, that will be telling you you lost 2 volts. Okay. And when we're talking about the critical frequency, that means at that frequency, the output will be what? At cutoff. Frequency, Vout equal. Remember this formula 0.707. Okay. V max. In this case, then you can see they can be maximum is 5 volts, then 5 times 0.707. Okay. You get 3.5.
So it's the half power one.
Okay. Now, at the cutoff frequency, they will be going down. Output go down. Okay, going down to what? Going down to 70.7% of the maximum value. That means 70.7% equivalent to 0.707. And 0.707 equivalent to how many dB?
3 dB.
Minus 3 dB. Okay? That means at the frequency, at the cutoff frequency, output going down minus 3 dB. That is the way you're talking. But the calculation, you cannot using minus 3 dB. You must be using 0.707. Okay? If you try to get the frequency higher than the cutoff, output keep going down. However, accepted will be after cutoff, they don't want any more voltage. Okay? So that's why you can see on this signal here. Okay, this is the gain go with the frequency. This is the frequency domain. This is supposed to be F here. Okay, 10 power of 1. What frequency is it? This is a 1, right? 10 power of 1. 10 power of 1 will be 10 hertz. 10 power of 2 will be 100 hertz. Of 3 will be 1,000 hertz, and so on. Okay? Now, this point right here, they say cut off frequency or critical frequency. Here, you see that? The thing is, they going down 3 dB. Okay? That means they going down to 0.707 of the maximum voltage. Okay? Then they will be going down here. You see that? Now I can pick up one point right here. Before we can pick a point right here, I want to asking you, what is the bandwidth for this one? That means right here. That means the bandwidth, okay, for 10 hertz, okay, that means the bandwidth will be at 10 hertz for 100 dB, okay, and the 100 hertz you cannot do anything. So now if I try to move up down here, you can see the difference. This will be also minus here, 3 point right here, dB. So the bandwidth will be going from here to here. They will be going into 1 kilohertz. They only telling you one thing. If you want the range of the bandwidth higher, wider, then the gain must be going down. Here is 100 dB, and now you pick in here, they got only 60 dB. If you pick up one point right here, so you can see the bandwidth go to the 10K. However, the gain going down to 40 dB. Okay, and finally at this point right here, what that means? Unity gain, unity gain. What gain equal?
1.
1.
Unity gain. 1 gain equal 1. And dB equivalent equal
0.
0. So that's why you're looking into here. Okay, this at the unity gain, and you're looking on a dB, they will be a 0. Okay, unity gain, that means input, output, the same. You have not lost anything. Okay. Now, first one, inverting operation amplifier. You don't have too much different amplifier. This is the first one. Okay. So on this op-amp here, they connect RF. RF they call a feedback resistor. Feedback means they connect from the output to the input of the op-amp. That's why they call a feedback resistor. Okay, and you get R in, you get V in, and 0 here, grounded. And right in the between V2 and V1, they call a V differential. Okay. Now, RF feedback resistor between output and inverting input to produce closed loop gain, ACL. ACL stands for closed loop gain. No current flow into the input terminal. That means the current cannot flow inside here. Okay. The different input is 0. VD will be equal V1 minus V2, and they be 0 volt. Okay. And the closed loop, if they calculate it, they will be equal RF minus RF divided RE. Okay. Now, I try to prove.
Why is the difference 0 volts?
Can you say again?
Yeah, why is the V diff 0?
That's what we're talking about at the beginning. The difference between the input positive negative will all the time will be 0. If it's not, then you have to going back at the beginning. Okay, we already said in here. Okay, the difference between VA and VB must be 0.
Why?
Okay, that's what I'm telling you. VD equal VSA minus VSB. Okay, and basically VD, that means equal V out divided to AOL, right?
Mhm.
V out divide infinity. That's why VD 0. VA minus VB equal 0. So that's why VA all the time equal VB. Only thing what I want to memorize that difference between input positive negative, they will be equal 0. Please, how come out of time it really? I try to get through that one. Now, I will try to prove for you how come we get the gain. First thing, this one ground, 0 volt here. And the difference between positive input, negative input is 0. That means if you get a 0 in here, then suppose you can get a 0 volt in here. That means this point, they supposed to be a 0. The thing is on this side is 0. Difference between in a positive, negative, 0, so that's why they equal. Only thing the difference is this 0 volt at this point, they not say ground, they call a virtual ground. Okay, that's just the definition. Now, what's the name for this ground? What you call this ground?
Physical ground, earth ground.
You can say physical ground. What that mean? That means you need a wire to connect to the route. But this point you not connect to the route using the wire, but they still be 0 volt. That's why they get a special name, virtual ground. Okay. Now, you can see you get the voltage 5 volt, and you get the current flowing from here. That's what we call I. This current coming up to here. They can be go in here. They can be going up here. They can going down here. Now, how come they not going down?
Ground. There's no voltage different.
Exactly. They get the same voltage, right? So that's why they cannot flow. How come they not go inside? How come they not come inside here?
No current, no voltage.
Now, high input impedance.
The input impedance of the op amp is in of the ideal op amp
Yeah,
is infinity.
it's
Yeah, it's too high.
too high. So that's why I cannot go here. So they will be going up here. When they come up here, positive here and negative here. Okay, then they go this way. Now, this is the negative here, and this side must be also the negative, right? This take like the wire connected. So if you say negative here, then they have to be negative here. And for RL here, you get a negative here, the other side must be positive. Okay? So this current going down up to this point, where they go? First thing, they cannot going down. Why?
Higher potential.
The thing is, this a negative, this a positive. Current have to be flowing positive to negative. So that's why they not coming down, they coming in here. Okay? In this case, they call a sink current. That means the op-amp pull the current into the op-amp. Okay? And also you can get the current IL, the load current. When they going up to this point, they will be go inside here. So this will be IL. So I and IL, you can see this is the I. This is the IL. So output of the op-amp current will be equal I plus IL. Okay? Now, if you want to calculate the V out, then V out equal what? You can say V out equal IL time IL. That V out mean from here to here, and they supposed to be negative. The thing is you get a negative right here. If you want to calculate the V out, that means V out from the V output to the route. So if you get IL, you can multiply by IL, you can get the V out. However, load did not depend on the circuitry, so they don't want to do this way. And I can tell you, V out means measured from output to the route here, or maybe from the output.
Are you in pain again?
What I'm saying is, V out
Because you're
means
moving up because you're coughing.
V out means measured from the output here to the route. Okay? Or you can measure from output here to the route here. Same thing. See that? That's telling you RL and RF look like they in parallel. Now, we're doing calculation. You want to get a formula for the circuitry, you cannot using a load. So I can say V out equal, you measure from here to route. They have to be minor. The thing is current and the voltage different polarity. I time F. That means V out. What I equal?
You know what? I'll give you mine, then I'll make small.
You can see the current I right here. And this is a 5 volt V in. And this route right here, then you can easy to find by the Ohm law. Okay, you take V in divide R1. Okay, if not right, let me know. Okay, the thing is on this point, you route it so you can get only one power, one resistor. You can calculate the current I. So now you can substitute I into V out. Minus I want to using V in divide R1 times RF. Okay, and if you want to calculate the gain, okay, ACL, that means closed loop gain. Okay, they can be equal V out divide to V in, and that means equal minus RF divide R1. This is the formula to calculate the gain for inverting amplifier right here. Okay, so they can calculate the gain by take 1.5 K divide 1K. This is 1.5 K. So that's why that's minus 1.5.
Can you mute the mic?
Oh. Yeah.
Mr. Pham, one question.
Yeah, hold on.
One question.
Yeah.
When you measure V out, you
Okay, turn on your mic.
when you measure the V out, you put the black lead at ground and you put the red lead where you got V out is at. Is that correct?
Correct.
But you'll be measuring across that resistor RL. Is that correct?
Right. That means if I ask you measure, connect DMM high side to here, low side to ground.
Okay. Only reason I was asking because you the ground is positive and the outside is negative.
That's why you get negative voltage.
So when the current come out of the loop, does no current goes into RL? Is that correct?
Exactly. For this case, okay, they will be a single current. That means the op amp pull the current into it.
Okay.
When we say short current, that means the op amp will be send the current out, so they can go down to the load.
So is the sink current, is that like an artificial current?
Yeah, that's to put it in. Put it into the op amp inside.
Okay, thank you very much.
Okay, now, what I say here is whenever you want to calculate the output or the gain of the inverting amplifier, that fixed, okay, equal RF minus RF divided to R1, okay? In this example here, they using RF and they using R2. Then I can put in here, same thing, this will be R2, okay? Normally, at work, you cannot see any RF. They have to be R1, 2, 3, 4, 5, 6. They don't care about RF, okay? And then if you get the gain, you want to calculate the V out, then you take the gain time to the input 5 volt here, you get minus 7.5 volt. If you get a load current, okay, that means the load current, you already get the V out, you already get the RL, you take V out, divide to RL. That's how come you get the load current. Adding load current into the I current here, you get op-amp current. So this is basically giving you every calculation regarding into this circuitry. Okay, so I can stop here until Wednesday. Okay, I recommend you try to reading ahead. Okay, that will help a lot to understand. This more easier than the transistor. Okay, any question?
Thank you.
Okay,
I'd like to hear an explanation again of the virtual ground. Why is there a virtual ground?
why we call a virtual ground? You can see the difference. Okay, they will be 0 volt. but
Can you
still
can you mute the other people?
just a minute.
Thank you. Thank you.
Okay, the big difference between the physical ground and virtual ground. A virtual ground, the current can go through it. That's it. That means the current can flow through the virtual ground. Physical ground not. That's why they call a special name, virtual ground. They 0 volt, but current still can flow through it.
But why is it a virtual ground?
Now that is the, you learn the op-amp, then you must be understand they call it, that is a virtual ground. We not make it up. They try to make the difference between physical ground and the virtual. Virtual ground is,
I guess the question I'm asking is, I don't want to memorize it. I want to understand it.
I don't
And-
understand either.
And the way I understand it is that if there's any difference between the non-inverting input and the inverting input and the non-inverting input, because the ideal op-amp has infinite gain, the output voltage would try to be infinite, but the output voltage is fed back to the inverting input to drive the inverting input to make the difference 0. So it's a very dynamic thing. It's like, because you have feedback and infinite gain in the ideal operational amplifier, you have to have 0. VD has to be 0. Otherwise, the output would be infinite. That's my understanding of why an operational amplifier in a feedback configuration has to drive VD to 0. Otherwise, the output would be infinite.
Okay, you can get more if you can read in detail. However, what I want you guys to understand is we want op-amp VD all the time will be 0. And also, in this case, you can get a virtual ground. They will be asking you, okay, the name of that route, then you have to know that it's a virtual route. How come they be different name with the physical route? The thing is the current still can flow through that route.
Right, so you can calculate the currents through R1 and RF by assuming that the virtual ground is 0. So that I in is equal to Vn over R1, and RF is equal to V out over RF, because the virtual ground, the potential at the virtual ground is 0. Right?
Right. Now,
Right.
I can have this one. Okay, so what different name?
Um, it's a differential amplifier.
So now this is connected to the negative also, and we can say VD here will be 0.
The virtual grounds at 10 volt.
So that not mean they be virtual route. No, they only virtual route if the other side connect to route.
Right.
Okay.
So the inverting input is forced to 10 volts.
If you're talking about this one, this is 10 volt right here. For example,
Yes.
I just bring it up to make sure you understand why virtual route. That means that this side must be route in order to get a virtual route. Okay?
If we're done, can I share something that I did with this presentation that might help?
Yet, for the people, they can know a little more thing, and also we can try to explain to them what they need to memorize. Okay? The thing is, we cannot go into too much detail when we don't need it.
Understood.
Okay? So we see you guys Wednesday.
Thank you.
You are welcome.
Thank you. Good night.
Good night, sir. Good night.
Good night.
18 hours today, right?
Hey,
bad.
we're just we can go over some of this stuff in the study group tomorrow. And I have I think I have a good explanation of why the gains are what they are for the inverting and non-inverting amplifiers that might be informative.
Won't we do it now when we got fresh brains?
Well, okay, if we're still
Good
open,
night.
okay, are we still open? Okay.